So now that we have the language of similarity at our disposal, let's talk about the concept of diagonalization. So by definition, we say that a matrix A is diagonalizable if A is similar to a diagonal matrix. So if we unpack the definition of similar and the definition of diagonal, what this definition says is that diagonal means that it's possible to write our matrix A as P times D times the inverse of P. And here, the stipulation is that D must be a diagonal matrix. Now, I want to issue a word of warning. The nomenclature that the author of our book, Strang, uses is Strang writes X times capital lambda times X inverse when he's referring to the diagonalization process. There's no content difference here. This is strictly just a difference in notation. The modern notation P times D times P inverse is more in vogue these days. So let's look at an example to illustrate this idea. So here, what we have is a factorization of a 3 by 3 matrix A as P times D times P inverse. And here, D is a 3 by 3 diagonal matrix. As soon as someone hands us this factorization, we immediately know that A is a diagonalizable matrix because it is similar to this particular diagonal matrix. Now, since we understand the concept of similarity, there's all sorts of interesting things we can say about A because working with the matrix D is very easy. Since D is a diagonal matrix, we immediately know what its eigenvalues are. They're -7 and 4. And the eigenspaces are easy to calculate too. If we subtract -7 from the diagonal of this matrix, we get 0, 0, and then 11. So the eigenspace of D for lambda equals -7 is spanned by the two vectors 1, 0, 0 and 0, 1, 0. So finding this particular eigenspace for D is quite simple. And the other eigenvalue of D is lambda equals 4. And to find its eigenspace, we would subtract 4 from the diagonal entries of D and find a basis for the null space of whatever's left over. Well, when we subtract 4 from -7, we get -11, -11, and then we get 0. So the eigenspace of D for lambda equals 4 is spanned by the vector 0, 0, 1. Well, what is this telling us? Well, since we understand the eigenvalues and eigenvectors of D, it's not difficult to understand the eigenvectors and eigenvalues of the matrix A. A will have the exact same eigenvalues, -7 and 4, but it does have different eigenvectors. To find the eigenvectors of A, we take our bases for the eigenspaces of D and multiply each of those vectors by the matrix P. Well, when we multiply our matrix P by 1, 0, 0, all we're really doing is plucking out the first column of P, and we get 1, -1, 0. When we multiply P by the vector 0, 1, 0, all we're really doing is plucking out the second column, which is -1, 2, -1. And so that's the first thing to note, is that for the eigenspace of A, where lambda equals -7, our two basis vectors can be chosen to be the first two columns of P. The other eigenvalue of A must be lambda equals 4. And to find a basis for its eigenspace, we look at the basis vector for the eigenspace of D, where lambda equals 4, and we multiply it by our matrix P. Well, when we multiply the vector 0, 0, 1 by our matrix P here, all we're really doing is plucking out the third column, which is the vector 1, -3, 3. So for our last eigenspace here, we can choose a basis vector to be the third column of P. So in this similarity relation, where A is expressed as a similar matrix to this diagonal matrix D, there's a very clear way to read the data for the eigenvalues and eigenvectors of A. The eigenvalues of A are located on the diagonal of D, and the eigenspaces of A are spanned by the columns of P corresponding to the appropriate entries on the diagonal of D. So since -7 is the first two entries on the diagonal of D, our basis vectors for the eigenspace of A, where lambda is -7, consist of the first two columns of P. And since the third diagonal entry of D is the eigenvalue lambda equals 4, our basis vector for the eigenspace of A, where lambda equals 4, should be given by the third column of P. There's a typo here, and this subscript D should say A here. I'll fix that in the actual slides. Okay, now I do want to point out that diagonalizability has a definition. By definition, a matrix is called diagonalizable if it is similar to a diagonal matrix. A natural question to ask is whether or not every single matrix is diagonalizable. And I want to illustrate that I want to show here that the answer to that question is actually no. Here we have a matrix A, and the columns are 0, 0, and 1, 0. This is an upper triangular matrix, so the eigenvalues are just both equal to 0, which means the characteristic polynomial of this matrix is simply equal to t squared. So, according to our discussion from the previous example, if A were diagonalizable, the diagonal entries of D would have to consist of the eigenvalues of A, and the eigenvalues of A are both equal to 0. So D would have to be the 0 matrix. But this is an issue because if A could be written as P times D times P inverse, the fact that D has to be the 0 matrix would tell us that A would have to be the 0 matrix, which is certainly impossible because A has a 1 in the upper right-hand corner. So this argument tells us that the matrix A here, although it's a perfectly good 2 by 2 matrix, is an example of a matrix that is not diagonalizable. So this example illustrates that some matrices are diagonalizable, but other matrices are not diagonalizable. So some matrices are not diagonalizable. So the question to follow up then is, well, how can we determine whether or not a given matrix is diagonalizable? And it turns out that there are tests for diagonalizability. One thing we know about the geometric multiplicities of a matrix is that if we add all of them together, we will never get a number bigger than the size of a matrix, but we might get a number smaller than the size of a matrix. It turns out that the property of being diagonalizable is the same property of being able to sum all of the geometric multiplicities of the eigenvalues for a matrix and that number equaling the size of a matrix. So we can test whether or not a matrix is diagonalizable, but by finding all of the eigenvalues, summing all of the geometric multiplicities, and checking that that number is equal to the size of a matrix. There's an equivalent way to check for diagonalizability, and that is to recall the notion that the geometric multiplicity of an eigenvalue can never exceed the algebraic multiplicity. So another way that we can check whether or not a matrix is diagonalizable is by checking that every eigenvalue has geometric multiplicity equal to the algebraic multiplicity. So this gives us two different ways to check whether or not a matrix is diagonalizable. We can either find all of the eigenvalues, sum all of the geometric multiplicities, and check that that sum equals the size of the matrix, or we can find all of the eigenvalues and check that each geometric multiplicity matches the algebraic multiplicity. Which test we choose to use depends on the context. If we are in a situation where we happen to know the algebraic multiplicities, maybe we'll use the second version of the test. But if we're in a situation where we don't have the algebraic multiplicities, maybe the first version of this test is simpler. So let's see some examples. Here we have the data of a 3 by 3 matrix where someone is handing us the eigenvalues. So here the eigenvalues happen to be lambda equals -7 and lambda equals 19. Well, we can calculate the geometric multiplicity of these eigenvalues. The geometric multiplicity of -7 as an eigenvalue. Remember, this is the nullity of the difference between A and -7 times the identity. So what we do is we subtract -7 from the diagonal, which is the same as adding 7 to the diagonal, and we check the nullity of the resulting matrix. Here, because the matrix is 3 by 3, figuring out the nullity isn't incredibly difficult. All we really need to do is find the rank. And one thing to notice is that the rank is guaranteed to not be 3, because since -7 is an eigenvalue, here we have to be working with a singular matrix. And we also see here that the rank is certainly not equal to 1, because the first column is not a multiple of the second column. So the rank here has to be equal to 2, which forces the nullity to equal 1. We can also calculate the geometric multiplicity of 19 as an eigenvalue of A. To do that, we go through the same procedure. We subtract 19 from the diagonal of our matrix, and then we figure out the nullity of the resulting matrix. Here, we find that the rank of the resulting matrix is actually equal to 1, because each column of this matrix is a multiple of the first column. Well, once we know that the rank of this matrix is equal to 1, we know that the nullity is forced to equal 2. So the geometric multiplicity of 19 as an eigenvalue of our matrix is equal to 2. So now, since we have both eigenvalues, and we found both geometric multiplicities, we can add these geometric multiplicities together, and we get 1 plus 2 equals 3. But 3 here is also the size of our original matrix, so this tells us that the matrix we're working with in this example is diagonalizable. So to summarize this example, we started with a 3 by 3 matrix. Someone gave us the 2 eigenvalues of this 3 by 3 matrix. We determined the geometric multiplicities of these 2 eigenvalues. When we added them together, we got the number 3. And since our matrix was 3 by 3, that tells us that this matrix is diagonalizable. Let's look at another, maybe larger example. Here, someone is giving us a 4 by 4 matrix, and they've also managed to factor the characteristic polynomial of this matrix. So the characteristic polynomial of this 4 by 4 matrix is t minus 3 quantity squared multiplied by t plus 4 quantity squared. Well, what is this telling us about the structure of the eigenvalues of this matrix? This is telling us that our 4 by 4 matrix has 2 eigenvalues, 3 and -4, and both of these eigenvalues have algebraic multiplicity equal to 2. So let's look at the geometric multiplicity of lambda equals -4 as an eigenvalue of this matrix. Again, to figure out the geometric multiplicity, what we do is we subtract -4 from the diagonal of our matrix, and we look at the nullity of the resulting matrix. This example was large enough that I couldn't necessarily see this just by eyeballing it, so I went ahead and I did some row reductions to figure out the nullity. When I did the row reductions, I found that the difference matrix has 3 pivots and 1 non-pivot column. This tells us that the nullity is equal to 1, and the idea here is that 1 is less than the number 2, which is the algebraic multiplicity of -4 as our eigenvalue. So the geometric multiplicity of -4 is equal to 1, but the algebraic multiplicity is 2. Since these numbers are different, our test for diagonalizability tells us that this matrix is not a diagonalizable matrix. So this gives 2 different examples of using our 2 different tests for diagonalizability. In this example, we found that one of the eigenvalues had a geometric multiplicity that was smaller than its algebraic multiplicity, and our test for diagonalizability says that means that our matrix is not diagonalizable. Okay, so let's finish this lecture by finishing the factorization. So the final question to ask here is, well, how do we find our desired factorization? So let's say that we take a matrix and we apply our test for diagonalizability, and we find that the answer is yes, the matrix is diagonalizable. Well, how do we find the factorization A equals P times D times P inverse? Our previous discussions say that this isn't new. although it is a new packaging of an older problem. We know that the diagonal entries of our diagonal matrix D should be home to the eigenvalues of our matrix, and the columns of P should give us bases for the individual eigenspaces of our matrix. So let's state this as an algorithm. So I like to call this the diagonalization algorithm. To diagonalize an n by n matrix A, let's start with two empty n by n matrices, P and D. In step 1, we find the eigenvalues of A and test whether or not A is diagonalizable. Remember, there are two ways to do this. We can either check that each geometric multiplicity matches the algebraic multiplicity, or we can sum the geometric multiplicities up and check that the sum is equal to the size of the matrix. Now, of course, if our matrix fails the diagonalizability test, it's impossible to find our factorization A equals P times D times P inverse. So we terminate the algorithm here. But if the matrix does pass the diagonalizability test, now what we do is we loop through the eigenvalues. So we go to each eigenvalue lambda, and we do a few things. The first thing we do is we find a basis for the eigenspace of A for lambda. And let's say that that basis is of the form v1, v2 up to vd. Well, the next thing we do is we insert those basis vectors into the next available columns of our matrix P, and then we insert the eigenvalue lambda on the diagonal of the matrix D, exactly D times little d, where little d is the dimension of our eigenspace. At the end of doing this procedure for each eigenvalue, we produce our diagonalization formula. A will equal P times D times P inverse. So let's look at an example here. So here we have a matrix A, and for this matrix A, I went to the trouble to find bases for the two eigenspaces of this matrix. So I found, I took A and I found that the two eigenvalues of this matrix are -7 and 18. And then I also found bases for the eigenspaces. I found that the eigenspace of A for the eigenvalue -7 is spanned by two vectors, 1, 0, 0, and -1, 1, 1. And I found that for the second eigenvalue, lambda equals 18, the eigenspace is spanned by one vector, 0, 1, 2. Well, according to the algorithm from the previous slide, I can use this information to build my matrices P and D. So for lambda equals -7, I found that my eigenspace was spanned by 1, 0, 0 as the first basis vector. So I insert that into the first column of P. And then I insert 1, -7 onto the first diagonal entry of D. And then I found that my second basis vector for the eigenspace where lambda equals -7 is the vector -1, 1, 1. So I put that into the second column of P. And then I put another copy of -7 onto the second diagonal entry of D. Now I move to the second eigenspace of this matrix where lambda equals 18. When lambda equals 18, I only have one basis vector, 0, 1, 2. So I take that basis vector and put it into the last column of P. And then in the last diagonal entry of D, I put the eigenvalue lambda equals 18. So what we're finding here is that D is organizing all of the eigenvalues, accounting for their multiplicity, and then P is matching those eigenvalues to the basis vectors of the corresponding eigenspaces. So at the end of this process, it turns out that A is guaranteed to equal P times D times P inverse. Now, one thing I'd like to point out is that the ordering of the columns in P and the diagonal entries of D are not mandated. So we just previously found that we could order the columns of P as this red column, this blue column, and this green column. And then the corresponding eigenvalues in D would be this red -7, this blue -7, and this green 18. Well, if you want to, you can shuffle around the columns inside of P. So we can instead choose P to equal this blue column, this red column, this green column. But if we do that, we should also shuffle around the diagonal entries in D appropriately. So if we're writing P in its columns as blue, red, green, we should write the entries of D as blue, red, green. Now, in this example, we're simply swapping the red 7 with the blue 7. So the matrix D doesn't actually change, but I still find this useful to think about because if the numbers were different, then the numbers would change. If we wanted to, we could write P as green column, blue column, red column. And if that's the case, then we need to alter D as well and write it as green number, blue number, red number. So now D looks like 18, -7, -7 on the diagonal. And if you wanted to, you could also write P as blue column, green column, red column, in which case D would need to be blue number, green number, red number. So D would have the diagonal entries -7, 18, -7. I think this last factorization, although valid, is probably a little bit less useful because here we're separating the eigenvalues on the diagonal, and that's a little bit more painful to work with, but it is still a valid diagonalization of our original matrix. So this sort of example is illustrating that our diagonalization factorization is not unique in general. Another thing I want to point out is that there's no reason that we couldn't work with complex numbers that aren't real to do this process. Here we have an example where someone has taken a 2x2 matrix and found its two eigenvalues, which happen to be -I and I, and someone also found bases for these eigenspaces. For lambda equals -I, we have a one-dimensional eigenspace spanned by the vector 1, -I, and for lambda equals I, we have another one-dimensional eigenspace spanned by the vector 1, I. Well, here we have a 2x2 matrix with two eigenvalues, and the geometric multiplicities sum to 2. So this matrix is certainly diagonalizable, and we can produce a diagonalization, A equals P times D times P inverse, by looping through the eigenvalues, inserting our bases for the eigenspaces into the columns of P, and then inserting the eigenvalues into the diagonal of D the appropriate number of times. So here our first eigenspace is spanned by the single vector 1, -I. So let's put that into the first column of P. The corresponding eigenvalue here was -I, so let's put that into the first diagonal entry of D. That finishes the first eigenspace. Now we proceed to the second eigenspace, which is spanned by the single vector 1I. So let's put that into the second column of P. And here, the corresponding eigenvalue is I, so let's put that into the second entry on the diagonal of D. This concludes our diagonalization of this matrix A, and this example is of note because here we're diagonalizing A using complex matrices that aren't necessarily real.